Imagine trying to put together a giant puzzle, but some of the pieces are invisible. You can see their effects, the gaps they create, the way they influence the pieces around them. But those pieces themselves, they just stay hidden.
Yeah.
That's the mystery we're diving into today, dark matter. This unseen force that makes up a whopping 27% of the universe. Welcome to Cosmos, an applied space and astronomy series.
Yeah, it's a fascinating puzzle. And it's one that has had astronomers and physicists scratching their heads for decades now.
Okay, so before we get lost in this cosmic fog,
hmm
can you help me understand this? We can't see dark matter, we can't touch it, but we're pretty sure it's out there. What's the evidence that we're not just chasing shadows here?
One of the most compelling pieces of evidence comes from looking at the way galaxies rotate.
Okay.
We can measure the speed of stars orbiting the center of a galaxy, and based on the visible matter that we see, stars, gas, dust, we'd expect those stars farther out to be moving slower,
Right.
just like planets in our own solar system. But that's not what we observe.
So the galaxies are breaking the rules then. What are they doing instead?
The stars in the outer regions of galaxies are moving much faster than they should if we only account for the visible matter.
Oh, wow.
It's as if there's some invisible mass,
Yeah.
like a halo surrounding each galaxy, providing this extra gravitational pull to keep those speeding stars in orbit.
Okay, so we've got these speedy stars hinting at something unseen. Are there any other clues that point towards dark matter's existence?
Absolutely. Another piece of evidence comes from the way light bends as it travels through the universe. This is called gravitational lensing,
Uh-huh.
and it's a direct consequence of Einstein's theory of general relativity. Massive objects like galaxy clusters, they actually warp the fabric of space-time around them.
Wow.
And this warping, it bends the path of light passing nearby.
So it's kind of like a cosmic magnifying glass then, distorting the images of distant galaxies.
Exactly. And by analyzing these distorted images, we can actually calculate the amount of mass that's bending the light. What's fascinating is that the amount of bending that we observe is far greater than what we would expect from just the visible matter in those galaxy clusters.
Wow.
So again, it points towards this presence of a significant amount of unseen mass, dark matter.
It's starting to feel like the universe is playing a cosmic game of hide and seek with us. So let's get to the heart of the mystery here. What could this elusive dark matter actually be made of?
Well, that's the million-dollar question. And it's a
Hmm.
question that has led to a whole bunch of fascinating and sometimes mind-boggling theories.
Yeah, can you walk me through some of the top contenders on this cosmic suspect list?
Sure. One of the most popular suspects is a class of particles called WIMPs, weakly interacting massive particles.
Winks.
Now, these are hypothetical particles, meaning we haven't actually directly observed them yet.
Okay.
But they fit nicely into certain theoretical frameworks that attempt to explain some of these unanswered questions in particle physics.
So WIMPs could solve multiple mysteries at once then. That's pretty cool. What makes them so difficult to detect?
Well, their defining characteristic is right there in the name weakly interacting. They're thought to interact very weakly with ordinary matter and light, primarily through gravity.
Oh, I see.
They're kind of like cosmic phantoms, passing through us and everything else without leaving much of a trace.
So they're there, but incredibly elusive. Are there any other suspects in this cosmic lineup?
There is. Another intriguing candidate is the axion.
Okay.
Another hypothetical particle, axions, are theorized to be incredibly light, much lighter than even electrons.
Wow.
And they interact even more weakly than WIMPs.
Okay, so if WIMPs are like phantoms or axions more like wisps of smoke, then...
It's a good analogy. Now, one of the reasons axions are so fascinating is that they were originally proposed to solve a different problem in particle physics called the strong CP problem. It's a bit technical to get into here, but essentially it has to do with why certain nuclear interactions don't violate a fundamental symmetry of nature called CP symmetry.
So axions could be tying together seemingly unrelated areas of physics. That's pretty neat. Are there any contenders that are a bit more grounded in what we can already observe?
Well, there's a category called MACHOs, massive compact halo objects.
Machos.
These are objects made up of ordinary matter, things like rogue planets, dim stars, or even black holes that might be lurking in the halos of galaxies.
Okay.
The idea is that if there are enough of these machos, their combined mass could account for some or even all of this missing mass.
So instead of some exotic new particles, it could just be a bunch of familiar objects hiding in the dark.
That's a possibility. However, observations and calculations suggest that machos alone can't account for all the dark matter that we infer. It's likely a combination of different things, both the familiar and the yet to be discovered.
This is getting pretty complex.
Ah.
Are there any other suspects on this dark matter most wanted list?
Oh, there are many. Another intriguing candidate is the sterile neutrino.
Sterile neutrino.
Oh, you're probably familiar with regular neutrinos, those incredibly light, almost massless particles that zip through the cosmos, rarely interacting with anything.
Yeah, I remember you mentioning them earlier when we were talking about WIMPs.
Right, they are indeed weakly interacting as well.
Yeah.
Well, sterile neutrinos are a hypothetical type of neutrino that are even more elusive. They wouldn't interact with the weak force like regular neutrinos, only through gravity, making them incredibly difficult to detect.
Wow.
However, some theoretical models suggest that they could be produced in the early universe and contribute to the dark matter puzzle.
So we have these hypothetical particles, WIMPs, axions, sterile neutrinos. They seem to be the prime suspects. Are there any other radically different approaches to solving this dark matter mystery?
There are. Some physicists believe that we might not need new particles at all. They propose that our understanding of gravity might be incomplete. Perhaps instead of invisible particles lurking in the shadows, it's the force of gravity itself that behaves differently on galactic scales than we currently predict.
So instead of adding new ingredients to the cosmic recipe, we might need to tweak the cooking instructions.
Precisely. This approach is known as modified Newtonian dynamics, or MOND for short.
MOD.
These theories try to explain the observed discrepancies in galaxy rotation without invoking dark matter. They suggest that gravity's pull might be stronger than predicted by Newton's law of universal gravitation at extremely low accelerations, which are typical in the outer regions of galaxies.
So instead of needing this halo of dark matter to keep those stars speeding along, gravity itself gets a boost in those outer regions.
Exactly. And some of these MOND theories even try to fit within the framework of general relativity, offering an alternative interpretation of the gravitational lensing observations we discussed earlier.
It's fascinating how the same set of clues can lead to such radically different explanations. It seems we have a classic scientific showdown brewing new particles versus new physics. How do scientists go about testing these competing theories?
It's a multifaceted battle fought on many fronts, from deep underground laboratories to space-based observatories. One approach is direct detection, where scientists are literally waiting for a dark matter particle to bump into a detector.
So it's like setting a cosmic trap and hoping something invisible stumbles into it.
In essence, yes. These detectors are often located deep underground to shield them from cosmic rays and other background noise. They use incredibly sensitive instruments to detect the faintest recoil or energy deposit that would occur if a WIMP or another weakly interacting particle collided with an atom in the detector.
What about those lighter, even more elusive candidates like axions and sterile neutrinos? How do scientists try to catch those?
For those, we often rely on indirect detection. Instead of trying to catch the particles themselves, we look for telltale signs of their presence. For example, if dark matter particles can annihilate each other, this process could produce other particles like gamma rays or neutrinos that we can detect with specialized telescopes.
So it's like searching for the footprints left behind by a creature we can't see directly.
That's a great analogy. Scientists are looking for specific patterns or excesses in these cosmic signals that could betray the presence of dark matter interactions.
We've talked about detectors, hidden deep underground telescopes, scanning the skies. What other tools do scientists have in their arsenal to probe this mystery?
Particle accelerators like the Large Hadron Collider play a crucial role. These massive machines smash protons together at incredibly high energies, creating a shower of new particles. The hope is that some of these collisions might produce dark matter particles, allowing us to study their properties directly.
So if we can create dark matter in the lab, it could finally lift the veil on its true nature.
Exactly. And there are even more ambitious experiments on the horizon, like next-generation detectors that utilize quantum technology to achieve unprecedented levels of sensitivity. These detectors could potentially detect even the faintest whispers of dark matter interactions.
It sounds like the field is buzzing with activity. But even with all these efforts, dark matter remains a stubborn puzzle. What are some of the biggest challenges that researchers face in cracking this cosmic case?
Well, one of the biggest hurdles is the very nature of dark matter itself. It's incredibly elusive, interacting so weakly with ordinary matter and light that it's incredibly difficult to detect directly.
Yeah.
We're essentially trying to catch a shadow. And then there's the challenge of differentiating the signal from the noise.
What do you mean by that?
The universe is a noisy place. Cosmic rays, radioactive decay, even the faintest vibrations on the Earth's crust can create signals that mimic those we're looking for from dark matter. So scientists have to go to great lengths to shield their experiments and analyze their data meticulously to tease out any genuine signs of dark matter.
So it's like trying to hear a whisper in the middle of a hurricane.
A very apt analogy, and to make things even more challenging, there's the sheer diversity of possible candidates and theories. It's like having a 1,000-piece puzzle where you're not even sure what the final image is supposed to be.
That sounds incredibly daunting. It makes you wonder if all this effort is worth it. Why are we so obsessed with understanding something we can't even see or touch? What's the big deal with dark matter?
That's a question that often comes up, and the answer lies in its profound implications. Dark matter isn't just some esoteric curiosity, it's the cosmic scaffolding upon which the entire universe is built.
Can you elaborate on that? How does something unseen have such a monumental impact?
Imagine the early universe, a swirling soup of hot, dense gas. Now imagine trying to form galaxies from that chaos. It's like trying to build a sandcastle on a windy beach. Gravity wants to pull matter together, but the expansion of the universe and the random motions of particles are working against it.
There's a cosmic tug of war.
Precisely. And this is where dark matter enters the stage. Because it interacts primarily through gravity, it's less affected by those other forces. It's like a cosmic anchor providing the extra gravitational pull needed to overcome those disruptive forces and allow matter to clump together, forming the seeds of future galaxies.
So without dark matter's gravitational embrace, those early galaxies wouldn't have stood a chance.
Exactly. They would have been torn apart before they could even begin to form. And this influence extends beyond the early universe. Dark matter continues to play a crucial role in the evolution and structure of galaxies today.
How so?
Galaxies rotate, and without enough mass, they would simply fly apart due to centrifugal force. But we observe that galaxies are rotating much faster than they should based on the visible matter alone.
So dark matter provides the extra gravity to keep them from spinning themselves apart.
Precisely. It acts like an invisible halo surrounding each galaxy, providing the gravitational force needed to keep everything in check.
It's mind-boggling to think about this unseen force orchestrating the cosmos on such a grand scale. But I'm curious, what are the implications for us here on Earth? Does dark matter have any direct impact on our lives?
It's a fascinating question, and one that scientists are still exploring. While dark matter doesn't interact strongly with ordinary matter, there are subtle ways it could influence our planet. For example, some theories suggest that dark matter particles passing through Earth could occasionally interact with atoms, potentially causing tiny temperature fluctuations or even triggering mutations in DNA.
So dark matter could be playing a role in evolution. That's wild. But these interactions must be incredibly rare, right?
Incredibly rare indeed. The effects, if any, would be extremely subtle and difficult to detect. But even if its impact on our daily lives is minimal understanding, dark matter is crucial for understanding the universe as a whole. It's a fundamental component of the cosmic web, the intricate network of galaxies, gas, and dark matter that makes up the large-scale structure of the universe.
It sounds like we're just scratching the surface of this cosmic enigma. What's next in the quest to understand dark matter? What exciting discoveries might be lurking just around the corner?
Well, one avenue that holds a lot of promise is the development of even more sensitive dark matter detectors. For example, researchers are working on detectors that use liquid xenon or argon cooled to extremely low temperatures.
Wow.
The idea is that if a dark matter particle collides with an atom in these detectors, it would produce this tiny flash of light
Okay.
that can be picked up by these incredibly sensitive sensors.
This is like waiting for a faint spark in a vast, dark chamber.
Exactly. And these next-generation detectors are being designed to be even more sensitive than previous experiments, pushing the limits of our ability to detect those elusive whispers of dark matter.
We've also talked about space telescopes. What role do they play in this cosmic hunt?
Yeah, space telescopes offer a unique vantage point. They're above the Earth's atmosphere, which blocks many types of radiation, giving them a clearer view of the cosmos. For example, the Fermi Gamma Ray Space Telescope is searching for signs of dark matter annihilation in the centers of galaxies where dark matter is thought to be most concentrated.
So it's like having a cosmic spy satellite scanning the universe for clues.
A very apt analogy. And there are other exciting space missions on the horizon. For example, the Euclid Space Telescope, set to launch in the next few years, will create a 3D map of the distribution of dark matter across the universe by observing how its gravity distorts the images of distant galaxies.
It sounds like we're entering a golden age of dark matter exploration with new tools and techniques constantly being developed. But I'm curious, what would a definitive eureka moment look like in this field? How would we know for sure that we finally cracked the code of dark matter?
Well, there are a few different scenarios that would send shockwaves through the scientific community. One would be the direct detection of a dark matter particle in one of these ultra-sensitive underground laboratories.
Yeah.
If we can capture a WIMP or an axion and study its properties, it would be a game changer.
It would be like finally meeting the mysterious stranger we've been chasing for so long.
Exactly. Another breakthrough could come from particle accelerators. If experiments at the Large Hadron Collider or future even more powerful colliders produce particles that match the predicted properties of dark matter, it would provide strong evidence for its existence.
So we could create dark matter ourselves and study it up close.
It's a possibility that has many physicists incredibly excited. And then there's the possibility of observing a completely unexpected phenomenon that can only be explained by the presence of dark matter.
Like a cosmic smoking gun that points directly to dark matter's existence.
Precisely. It could be a new type of astrophysical observation or an anomaly in particle physics experiments that defies our current understanding and forces us to rethink our models of the universe.
It's incredible to think that we could be on the verge of such groundbreaking discoveries. It feels like we're standing on the precipice of a new era in our understanding of the universe. But I'm curious, what are some of the broader implications of solving the dark matter mystery? How would it change our view of the cosmos and our place in it?
The implications are profound. If we can definitively identify dark matter, it would not only fill a major gap in our understanding of the universe, but also open up entirely new avenues of inquiry. For example, if dark matter interacts through forces other than gravity, it would point towards new physics beyond the standard model, potentially leading to a revolution in our understanding of particle physics.
So it could rewrite the textbooks on the fundamental building blocks of the universe.
It certainly could. And understanding dark matter could also shed light on the evolution of the universe as a whole. It could help us understand how galaxies formed and evolved, how the cosmic web took shape, and perhaps even provide clues about the ultimate fate of the universe.
It's a reminder that even the most invisible things can have the most profound impacts. But I'm also wondering, what if we never solve the mystery? What if dark matter remains elusive, a cosmic enigma that continues to taunt us?
It's a possibility we have to consider. But even if we never definitively identify dark matter, the search itself is incredibly valuable. It's pushing the boundaries of science and technology, inspiring new generations of scientists, and forcing us to confront the limits of our knowledge.
It's a humbling reminder that there's still so much we don't know about the universe, and that the journey of discovery is just as important as the destination.
Absolutely. The pursuit of knowledge is what drives us forward. And who knows, perhaps the most profound discoveries are the ones we haven't even imagined yet.
It's been an incredible journey exploring the enigmatic world of dark matter, from its elusive nature to its profound cosmic influence. Thanks for guiding us through this cosmic mystery.
It's been my pleasure. And for those of you listening, if this deep dive into the world of dark matter has sparked your curiosity, I encourage you to delve deeper into the subject. There are countless resources available online in libraries and through science organizations. And who knows, maybe one of you listening will be the one to finally unlock the secrets of this cosmic enigma.
And that wraps up our exploration of dark matter for this episode of Cosmos in a Pod. Don't forget to follow and subscribe to Cosmos in a Pod on your favorite podcast platform so you don't miss our next cosmic adventure. We release new episodes every week, exploring all sorts of fascinating topics in space and astronomy.
And be sure to check out our YouTube channel for even more cosmic content, including stunning visuals, animations, and interviews with leading scientists.
Until next time, keep looking up and keep wondering. The universe is full of mysteries waiting to be uncovered.